interesting journey over the years with an array of satellites for communication, meteorological, remote sensing, navigation, scientific satellites, and when it comes to rockets like SLV, ASLV, PSLV, GSLV, and GSLV Mark III. These satellites and rockets have been built by different ISRO centers. India has joined an elite space club by launching Mars Orbiter mission in 2013 and made India the first nation to succeed in its maiden attempt to reach Mars. Another feather in ISRO's cap was added when the constellation of 7 satellites created India's very own satellite navigation system. On February 15, 2017, ISRO created history and a world record by successfully launching 104 satellites on a single mission, PSLV C-37. On November 14, 2018, ISRO successfully launched GSAT-29 from Sriharikota. The satellite weighing at 3,423 kilograms, it was the heaviest satellite to be launched by GSLV from Sriharikota. Keeping with India's emergence as an economic and technological powerhouse, ISRO is now working towards manned flight. Many technologies were demonstrated as a precursor to the first manned mission. The experimental mission that paved the way for human spaceflight mission was the Space Capsule Recovery Experiment conducted in January 2007. After the successful launch of Chandrayaan-2 on board the Mark III M2, ISRO now boasts an operational heavy lift launcher capable of putting a 10-ton spacecraft in lower Earth orbit. The maturity gained over the years in the launch vehicle area will be gleaned to engineer a human-rated GSLV Mk3 vehicle worthy of human spaceflight. ISRO is also taking the industry on board for increasing the capability to become a global hub for the space industry. With more than 108 satellites and 77 launch vehicle missions, ISRO has proved to the world that India is second to none in the application of space technology to the real problems of man and society. ISRO achieved
The GSLV Mark III, the third generation GSLV, inherits various technologies from its predecessors. It's very different in terms of its stages, structure, size, and has double the payload carrying capacity than the Mark II version. Nearly 43.5 meter tall and with a lift-off mass of 641 tons, ISRO's GSLV Mark III T2 is about to roar once again at the second launch pad at SDSC Shar.
Geosynchronous Satellite Launch Vehicle Mark III is the heaviest launch vehicle of India. GSLV Mark III is capable of lifting up to 4-ton mass to geosynchronous transfer orbit or a 10-ton payload to low Earth orbit. This vehicle is powered by 2 S200 solid motors, one L110 liquid core stage and a powerful liquid cryogenic stage C25. This mission is second developmental flight of GSLV Mark III, and this is important mission for GSLV Mark III program, as After this success of this mission, GSLV Mark III will be declared as operational and will join the group of operational vehicles PSLV and GSLV. The payload for GSLV Mark III D2 is a very advanced high throughput satellite GSAT-29, which is a multi-band, multi-beam communication satellite with a lift-off mass of 3.4 ton. GSAT-29 payloads are configured to cater to the communication requirements of users from Jammu and Kashmir and northeastern regions of India. Apart from these operational requirements, the satellite would be demonstrating several new and critical technologies also.
The first stage of this giant vehicle consists of two S-200 boosters, which are 26.2 meters long and 3.2 meters in diameter. Each has a capacity of carrying 205 tons of solid propellant. S-200 is the third largest solid rocket motor in the world. The L-110 core stage carries 116 tons of earth-storable liquid propellant. It is nearly 21.4 meters long and 4 meters in diameter. It employs two enhanced thrust Vikas engines. The 13.5 meter long indigenous C-25 cryogenic upper stage forms the third stage of the vehicle. It uses 28.6 tons of supercooled liquid hydrogen and liquid oxygen, which provides more thrust for every kilogram of propellant burned compared to conventional liquid propellants. On top of the third stage is the spacecraft in the 5-meter diameter payload fairing. The first successful experimental flight of GSLV Mark III took place in 2014 when it carried a crew module as its payload. Both its solid and liquid propulsion stages had performed well, and the vehicle was proven in the atmospheric flight regime. The first developmental flight of GSLV Mark III successfully launched India's high-throughput communication satellite, GSAT-19, weighing 3,136 kilograms on 5th June 2017. In this GSLV Mark III D2 mission, the rocket will carry the 3,423 kilogram GSAT-29 communication satellite into geosynchronous transfer orbit. GSAT-29 is a forerunner of future advanced communication satellites of INSAT and GSAT series. Its Ku and Ka band communication payloads are designed to mainly focus on providing high-throughput connectivity to the large population of the country, including the ones in hilly and geographically inaccessible areas of Northeast and Jammu and Kashmir regions. The satellite is also a test laboratory for several new technologies. It is a 3-axis stabilized geostationary satellite configured on ISRO's enhanced I-3K bus. The satellite has a multi-band, multi-beam payload, which is essentially meant for demonstrating new technologies. The Ku band payload of the spacecraft comprises transponders for Northeast and for Jammu and Kashmir regions.
Yeah. Okay, we'll start with the remaining of the session B. I think now Aditya, just to try.
Okay, sir.
Yeah.
Okay, sir.
Ah.
Okay, sir. Can you see my screen, sir?
Yeah, exactly. Now we can see. So now I welcome Aditya Jaiswal from Aries to present his paper on characterizing the layers of enhanced turbulence using VHF radar over central Himalayan site. Yeah, we can see your slide nicely. Now we can go ahead, Aditya.
Okay, sir. Okay. So, good evening, everyone. Myself, Adit Jaiswal. I am research scholar at Aries Nainital, and I will be presenting on the topic of characteristics of strong turbulence layer that were observed using VHF radar at our site, which is in the central Himalayan region. So, we have used the simultaneous observations from VHF radar and radio sonde to understand the nature of the persistent strong reflectivity layer in the lower troposphere, and we have tried to understand the instabilities that are generating the turbulence within these layers. Particularly, we will take up the case of the Kelvin-Helmholtz instability, and then we have estimated the energetics of turbulence within these layers. As we know that for the VHF radar, the primary mode of scattering is the Bragg scattering due to fluctuations in pressure, temperature, and humidity at the Bragg scale caused by turbulence. Hence, they have been the popular instrument for the turbulence studies. Our ST radar facility is located at a high altitude site of Nainital in the Himalayan foothills. It transmits at a high VHF frequency of 206.5 megahertz and has a wind profiling capability up to 20 km at high temporal and vertical resolution. For our study, we took these 6 days of observation where we had continuous observation with radar from 6 to 12 hours covering morning to evening period. Each day we also had co-located radio sonde observation and we validated the wind components of both instruments and found reasonable agreement between them. During observations, the vertical resolution of the radar was 75 meter and the first range gate was 375 meter above ground level and the resolution of the velocity was 0.05 meter per second. So, during our observation, we have observed various structure in the time height variation of the radar SNR.
Aditya, your
And
slides are not changing. Is this problem with us or anybody? LOC can confirm. Slides are changing?
No, slides are not changing on our side as well. So could you please
okay,
check that, Aditya Jaswal?
I'm currently at the fifth slide. Okay, this slide can you see?
Your screen is frozen from this side. So can you please stop sharing and start again?
Okay. Can you see it now?
Yes, we can see your screen, which is titled as objectives.
Okay.
Yes, the slides are changing now. So
Okay.
if you could go back a bit and start again, because
Okay. Okay, so we have used the simultaneous observation from VHF radar and GPS radio sonde to study the nature of the persistent layers of a strong reflectivity in the lower troposphere. And we have tried to understand the instabilities generating turbulence within these layers. And we have then estimated the energetics of turbulence within these layers. As we know that the dominant mode of scattering in the VHF radar is the Bragg scattering, which is caused by the turbulence. Hence, these type of instrument has been the popular instrument for the turbulence studies. So, for our ST radar facility is located at a high altitude site of Nainital, about 1.8 kilometer above mean sea level, and it operates at a high VHF frequency of 206.5 megahertz, and it has a wind profiling capability at high temporal and vertical resolution. And so, for our experiment, we have taken these 6 days of observation where we had continuous observation of the radar from 6 to 12 hours, covering morning to evening period, and we also had the co-located radio sonde observation on these days, and we compare the wind components of the both instruments and found reasonable agreement between them. And for these observations, the vertical resolution of radar was 75 meter, and the first range gate was 375 meter above ground level, and the velocity resolution of was 0.05 meter per second. So, we have during our observation we have observed the various kind of atmospheric structures in the time height variation of the radar SNR, and somewhere the convective plume type of uh, is, structure, somewhere the periodic wisp kind of structure, and then we have observed the uh, uh, fine layer and sheets type of structure with a lifetime duration of 3 to 5 hours, and some layers were observed throughout the observation, and some sporadic below type of structures are also observed. So to so find the uh, uh, why these kind of layers exist, we had look into the uh, background meteorological conditions that we got from the radius only observation. So here you can see the vertical profile of the square of band facial frequency, temperature, relative humidity, wind shear, graded Richardson number, and radar SNR. And you can here clearly notice that the high radar SNR occurs in the region where the humidity layer is trapped between the two temperature inversion layers. And we have also estimated the potential radio reflective index gradient from these MET variables, and it can be seen that it really follows the radar SNR pattern very well, and that shows the importance of these temperature and humidity gradients in the reflectivity of 200 megahertz radar. So during our observation, we have observed one event of KH instability. As we know that this is the dynamic instability that occurs in a highly sheared environment, in that occurs in a sheared flow in a hydrostatically stable environment, and and gentle waves forms at the shear interface, and they goes in amplitude, and 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 breaks away and generate turbulence. So with the fine temporal and vertical resolution of the radar, we observed we have observed the characteristic Bates pattern of the KH instability in the height region of 2.85 to 3.15 kilometer, that is about width of 300 meter, and uh, the the time difference between the crest of uh, each of uh, these periodic burst and reflectivity was found to be about 9.6 minutes. And then we checked the Richardson number in this height region, which was found to be between 0 and 0.25, which is basically the critical condition required for the generation of this kind of instability. So from the wind observation, it can be seen that the on the both sides of the below structure, there is a change in the wind direction, and there is a very strong speeds here, and which is basically due to the change in the speed and direction of the meridional component of the wind. Similarly, in the time height variation of the vertical wind velocity, we have observed the alternate upward and the downward motion inside the below structure, and there is a sudden rapid enhancement of the vertical velocity fluctuation inside the below structure, with the magnitude reaching as high as 0.75 meter per second. And then we have estimated the periodicity of these wavy oscillation of the vertical wind velocity, and found the mean period of oscillation about 10.4 minutes. So we wanted to know that whether this reflectivity pattern is due to turbulence, or is it due to some storm reflection from some stable layer. So we have calculated the aspect ratio by calculating in the ratio of SNR at the zenith and the off zenith, and we have found it to be either less than or equal to 1 in this region. That shows the turbulence was isotropic in the medium. Then we estimated the turbulence kinetic energy dissipation rate, and find the rapid enhancement in the in these below structures. So for the estimation of the turbulence, we have used the spectral width method. The advantage is that it only relies on the dye parameters only, and we have corrected the spectral width for the non-turbulent effect, that is the broadening due to beam width and the wind shear. So here I have listed out the magnitude of the TK displacement rate for all of these strong reflectivity layer for all the cases, and for the aviation purposes, the strength of the turbulence is characterized in terms of the eddy displacement rate that can be calculated for the TK displacement rate, and it can and here the if the value is greater than zero point 0.7, it is categorized as a severe turbulence, and it can be seen that for all the cases the turbulence in all these layers can be categorized in the severe category. To sum up, we have used a simultaneous observation from radar and radio sonde, and it revealed the layers of strong reflectivity in the lower troposphere, and that is corresponding to the humidity layers which are trapped between the temperature and inversion sheets. The first direct observation of the KH instability over Himalayan region was made using VHF radar, and the duration of the event was about 2 hours, and nearly same periodicity is observed in the radar reflectivity and the vertical wind velocity, that's about 10 minutes. In TK dispersion rate estimated using radar, the strength of turbulence is found to be severe in the high reflectivity layers for all the cases. Uh, Thank you very much for giving me the opportunity to present my work.
Thank you, Aditya, for a very good presentation. It was very nice to see the KHA below. Even though I worked with radar, this kind of a signature, first time I'm seeing. So thus now talk is open for questions. One question from the chat box from Dr. Siddharth Sankadas. Very good talk, and your
Okay.
ST radar performance looks too good. There are many data gap in your RTA plots that need to be shown instead of continuous plots.
Okay, sir. Okay.
So because there is some kind of a striations are there. So instead of that one, you can put white patches. That will be
Oh,
more better. That's what he suggests.
okay, sir. Okay, sir. I will do that. Okay,
Yeah.
thank you,
Any
sir.
other questions from audience? If there are no questions, I just want a suggestion. During December, January, February, you'll be experiencing subtropical jet, right? At 9 to 10 kilometer, I think, Nainital.
Yes, sir. Yes, sir.
Strong winds of like 50 to 60 meter per second. So
Yes,
around
sir.
the edges of this jet, you may get some this kind of a billows. Just to try out during the winter season. Huh?
Yes, sir. Yes, 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 sir. We will
Yeah.
keep looking for these signatures, sir.
Okay. Thank you, Aditya, for a very good talk.
Well, thank you very much,
Yeah.
sir.
Yeah. Now we will move on to the next talk. In the session, second session, this is by Shivali Verma. She'll be talking about aerosol cloud precipitation relationship under maritime and anthropogenic polluted condition. She's from National Remote Sensing Center, Hyderabad.
Good evening, sir.
Yeah.
So, can I share my presentation now?
Yeah, you can share your presentation.
So, is it visible?
Yeah, exactly. You have to go to full screen mode.
Okay. So, good evening, everyone. I'm Shivali Verma, and I'll be talking about aerosol cloud relationship under maritime and anthropogenic polluted conditions and
Shivali,
relationship with.
you have to put in a full screen mode. It is still in the
Sir,
other mode.
it is in the full screen mode, sir.
I think you have not shared the entire screen. That's why it is like this. Just unshare and again share it with the desktop. Full entire screen you have to share.
Okay.
Yeah. When you click the share button, you will be getting First left thing you have to select. Now
Yes,
go for
sir.
F5.
Is it fine, sir?
We can see your slides, but not in the full screen mode. In this mode, you cannot change the slides also, I think. For you, it is full screen there,
Yes, sir. It is full screen.
but here we are getting only. You just try to move the slide. We are not getting that.
No, is it
What
not
you shared,
visible?
you don't share the window. You share the entire screen.
Right. Okay.
Yeah. Choose the first option when you leftmost thing. Yeah.
Now is it
Now
fine,
we are
sir?
getting. Yeah. Go ahead.
Okay, so I'll be talking about aerosol cloud relationship under maritime and anthropogenic polluted conditions and relationship with the precipitation. Now, how important are clouds in the Earth's energy budget? The Earth's atmosphere energy balance is achieved as the energy received from the sun balances the energy lost by the Earth and back to space. So, in this way, the Earth maintains a stable average temperature and therefore a stable climate. So the energy that is released from the sun is emitted as shortwave and ultraviolet in ultraviolet range. But when it reaches the earth, some of it is reflected back and some of it is absorbed by the atmosphere and at the earth's surface. So when the flow of the incoming energy, solar energy, is balanced by an equal flow of heat to space, earth is in radiative equilibrium and the global temperatures are relatively stable. And anything that increases or decreases the amount of incoming or outgoing energy disturbs the earth's radiative equilibrium, and the global temperatures, they rise or fall in response. So we know that the albedo of the earth is 0.3, which means 30% of the incoming solar energy gets reflected back to space, and out of this 30%, 20% alone is contributed by clouds. So that is why we say that they are very important in the energy budget of the earth. Now, talking about the importance of cloud top temperature in the climate perspective, the study of clouds, where they occur, and their characteristics, it plays a very important role in understanding the climate change. When we see at the low level thick clouds, they primarily reflect the solar radiation and they cool the surface of the earth. And high level clouds that are present, they primarily transmit the incoming, high level thin clouds, they transmit the incoming solar radiation, and at the same time they trap some of the outgoing radiation emitted by the earth and radiate it back, thereby warming the surface of the earth. And whether the cloud will heat or cool the surface, it depends on various factors like the altitude where it is present and the size and the particles that are present in the cloud. So if there is a high level cloud, they absorb the earth radiation and they emit in long wave IR radiation, and both back to space and the earth. Because cirrus clouds, they are high, they are found in about 8 to 12 kilometers of altitude, and therefore they are cold, and the energy radiated to outer space is lower than it would be without the cloud. So the portion of radiation thus trapped and sent back to earth's surface adds to the shortwave energy from the sun and the long wave energy that is already existing, and this additional energy causes the warming. Whereas in case of the low level clouds, they cool the earth because they are much thicker, and they are not transparent, and they reflect most of the solar energy back to space. Although they also emit the long wave radiation, but they are near to the earth's surface, so and are almost at the same temperature, so they radiate at nearly the same intensity as the surface and do not greatly affect to the IR energy emitted to space. So therefore CTT is a very crucial parameter in estimating shortwave and long wave radiative effects of the clouds, by if we can confidently classify them in different categories. The radiative impact of different type of clouds vary depending on their properties, and hence accurate representation of clouds in climate models is essential for this realistic simulation of Earth's current and future climate. So continuous and detailed monitoring is very essential of cloud properties, and it is necessary to realistically represent them in models and understand the role in the weather and the climate system. So various studies have happened, like there's literature available globally which talk about the importance of cloud itself in the climate perspective. Moving on, talking about the retrieval algorithm using INSAT 3D. Now we know INSAT 3D is a geostationary platform, and the advantage of geostationary platform over polar is that we get continuous monitoring. And since cloud is very dynamic in nature, so continuous monitoring is very essential. So these are the channels that are available from INSAT 3D. 6 channels that are available, and the investigation of the CTT and its diurnal variation is highly reliant on high spatial and temporal resolution data. So an algorithm has been developed for detection of clouds and the retrieval of CTT from INSAT 3D. These retrievals, they are validated using the collocated ground-based measurements, and they are also intercompared with the collocated satellite measurements with the specific intent to generate climate quality data. An algorithm, this has been divided into two parts. One is the cloud mask retrieval and the other is the cloud top temperature. So cloud detection scheme is carried out by an integrated approach in which 9 different exhaustive tests are performed by grouping them into primary, secondary and semi-transparent cirrus clouds criteria. Primary test, it employs strict criteria to avoid any misclassification of clear pixel as a cloudy one, and such pixels are retrieved using the secondary test if in case they are missed, and pixels are identified as cloudy only if they are detected multiple times in the secondary test, and semi-transparent are detected by combination of two different tests using brightness temperature at TIR1, TIR2 and at water vapor. Then when such pixels are identified as cloudy pixels, they are subjected to a CTT retrieval scheme where it is characterized into 4 different categories. For high and low level opaque clouds, brightness temperature at TIR1 is itself as taken as cloud top temperature because the emissivity is nearly 1. And for semi-transparent and partial clouds, a method based on 2D scatter plot between brightness temperature at TIR1 and brightness temperature difference at TIR1 and TIR2 is used for CTT retrieval. So the performance of cloud detection and CTT algorithm is examined by comparing them with the ground data and with the satellite observations. Now, if we see here in the left side, the image, cloud mask image is shown where the white patches are the cloud mask, is the cloud mask data. And on these white patches, CTT retrieval has been performed. So on the right side, we see the cloud top temperature data. Because it is a geostationary platform and we get data every half an hour. So this is one sample GIF image which has been shown for cloud top temperature. Now this data can be found on the nicest platform of on Bhuvan platform, which is the Indian Geo platform of ISRO. It is a National Information System for Climate and Environment Studies. We can find it under NICES in the Atmospheric and Climate Sciences, cloud top temperature, cloud fraction, cloud mass, all the data which is climate quality data. Now, coming to the intercomparison and validation, this algorithm, when implemented on INSAT 3D channels, we have generated the cloud mask. This cloud mask has been compared with the MODIS cloud mask and Calypso with a hit rate of almost 80%, and the same algorithm has been implemented on MODIS similar channels which are like similar to INSAT 3D channels. And again, it has been compared with the MODIS existing cloud mask product in Calypso with a hit rate of almost 85%. And then the validation of CTT has been done using radio sonde at SHAR, Calypso data, and this hyperspectral microwave radiometer at NRSC Shadnagar. So for any parameter to be called as an essential climate variable, the Global Climate Observing System, that is a GCOS, has a certain requirement that the parameter has to meet in order to be called as an ECV, which is an essential climate variable. So the required measurement uncertainty for the cloud top temperature required by GCOS is within like 1 to 5 Kelvin, and we have achieved within 4 to 5 Kelvin. And the horizontal resolution required by them, spatial resolution, is 50 kilometers. We have at 25 and 50 both. And the temporal resolution required is 3 hourly, and the data is coming at half an hour interval. Now, this aerosol and cloud, like to understand the interactions of aerosol and cloud, we have taken the cloud top temperature data and cloud fraction, cloud mass data from INSAT 3D and used MODIS aerosol data. And the study region is over the Arabian Sea. And we see that with an increase in aerosol index from 0 to 0.6, there is an enhancement in cloud fraction that is seen in both polluted and maritime conditions in the months of January and December of 2018. Whereas cloud top temperatures have been seen to decrease when there is an increase in the aerosol index, that is in the pollution ridden conditions from 0 to 0.6 in both maritime and polluted conditions of January and December. This shows that there is a growth, horizontal growth in the cloud, and there is a vertical growth as well. Now, to observe this even further, the CF-CTT variations over pollution-laden regimes are showing a strong dependence on aerosol index, And if we see the plot over the right hand side, in between cloud top temperature and cloud fraction in January and in December, we see that there is a strong dependence on aerosol index as it increases from 0 to 0.6. There is a decrease in CTT is associated with enhancement of cloud fraction. So the filled circles that are shown here, they are the pollution laden conditions, and the circles which are not filled, they are relatively maritime conditions. This suggests that CTT and CF enhancements are correlated in pollution conditions, suggesting that CF-CTT variations are induced by aerosol interactions. So there have been literature that is available globally which has studied the aerosol cloud interaction, and also there are certain campaigns like IndoX and MAC campaign, etc., which have studied the interactions. So this has been published in IEEE TJRS. Then moving on to the cloud precipitation relationship, here this is an ongoing study, and we wanted to find out if cloud top temperature or the cloud data using a geostationary platform can act as a proxy to study the extreme weather events that happen over in India. So this event is actually is reported by IMD as an extreme weather event in Sambalpur, Odisha district, with the total rainfall of 622 millimeter on 22nd July 2018. So this is an image to depict, like, to show the cloud top temperature on that day at 00 UTC, and the IMERGE data, that is integrated multi-satellite retrieval from GPM, on 22nd July, and the diurnal variations, if we see, when the cloud top temperatures have been seen to fall below 200, and there is an increase in the rainfall as well. So we are trying to see if this can act as a proxy for to further say that this event will be going to be an extreme weather rainfall event. So similarly, we have also entered into collaboration with the IST, where we are going to study the cloud precipitation relationship from satellite as well as ground-based perspective. So from satellites, we'll be studying the spatio-temporal data, and we'll be studying the cloud top properties, whereas from the ground, we'll be hello.
Yeah, I think Saurita has started sharing. Her presentation is not over.
Should I share again, sir?
Yeah, I think so. Yeah.
Is it visible, sir?
Yes. Yeah. Go ahead. Yeah.
Okay, so from the ground based, and we want to examine like on a cloud by cloud basis, this both the cloud micro and micro physical properties, and that will help us to understand between precipitation and the extreme precipitation events. So, and we also have instruments like All Sky Major and Hyperspectral Microwave Radiometer at NRSC Shadnagar. Using them, we will be validating the cloud parameters for a climate quality perspective. So this is like hence this study, it adds to the existing studies in our understanding of the link between the processes with the availability of improved satellite data in terms of their accuracy and spatial temporal coverage to improve our understanding between clouds, precipitation, and aerosols. Thank you, sir.
Thank you very much, Shwali, for a very good presentation, and happy to know that your algorithm could track the cloud top temperatures and establish a relation between aerosol, cloud, and precipitation. Now, talk is open for questions. From chat box, there are no questions. If anybody have questions, please raise their hand and they can ask. So there are no questions. I have one question: whether your algorithm can differentiate between the high cloud and cirrus clouds, like deep convection and cirrus clouds?
Yes, sir. It can differentiate between them, sir.
Yeah, because both will be having a same kind of a cloud top temperatures, deep convection and cirrus. How you are? What is the condition you put to differentiate both?
Hello.
Hello. What are the
Sir.
conditions you put to differentiate deep convection and cirrus?
Sir, cirrus will come under the semi-transparent category, and deep convection will come under this the opaque cloud category.
No.
So based on
Sometimes
this,
we have a thick cirrus also during monsoons. That annuals of your deep convective clouds will have a very thick cirrus detached from the deep convection. Okay, you just look at it. This one. Okay, this aspect.
yes, sir.
Yeah. Okay. Thank
Thank
you.
you, sir.
Yeah. Next, we move on to the next talk by Saurit Saha from PRL. He'll be talking about unraveling the characteristic of atmospheric boundary layer over Ahmedabad. Saurit, now you can share your presentation. Yes, go to full screen mode.
Can you hear me? Hello?
We can hear you, but your presentation is not in the full screen mode.
Is it now in the full screen mode right now?
We are not getting. I think you have to share the entire screen. When you click the share button, the first option will be there, desktop. That you have to.
Okay. So please give me 1 minute. I'm sorry for the inconvenience.
Yeah, no problem. Yeah, you just try.
I'll do the entire screen, right?
Yeah.
Okay. I was sharing my window actually. So can you see my presentation right now in the full screen mode?
Yeah, exactly. Yeah, go ahead. Yeah.
Okay. Good evening. This is Saurita Saha. I'm working as a scientist C at PRL Ahmedabad. I am thankful to the committee for giving me this opportunity to present my work on this platform. Today, I will be talking about the atmospheric boundary layer over Ahmedabad, which is an urban location in the western region of India. Now, first, let us have a basic idea of the atmospheric boundary layer. It is basically the lowermost layer of the Earth's atmosphere, which is in contact with the surface, and it plays a major role in the energy and momentum exchange with the free troposphere, and it helps in the dispersion of pollutants. The boundary layer is majorly driven by solar energy, terrain, and surface friction, and it can be affected by turbulence, convection, and winds. Now, let us look at the importance of boundary layer. It basically influences the hydrological cycle. It helps in dispersion of the pollutants and trace gases, as I mentioned earlier, and it also helps in the kinetic energy dissipation. Now, this is a figure that I have taken from the atmospheric boundary layer over Ahmedabad, and this shows the constituents of the atmospheric boundary layer and how it is varying during the day. Now, the boundary layer, it has during the sunset, during the sunrise, the boundary layer rises and reaches the maximum mixed layer height at around 15 hours local time, and then it reduces and it forms the stable layer. The residual layer, you can see it in this figure. Now, for this study, we have used a ceilometer to characterize the boundary layer, and we have implemented the gradient method to calculate the boundary layer height. Now, in this method, what we do is we find the gradient change in the aerosol concentration, and when we see a negative peak, like when we see a negative peak, we find that we can assume that the boundary layer is there. So basically, what happens? The aerosols are most of the aerosols are there in the boundary layer of the atmosphere. They are packed in the boundary layer. So when there is a concentration change in the aerosols, we know that there is a boundary layer. Now, in this study, we have done a year-long analysis of the atmospheric boundary layer using ceilometer data to find the characteristics of the boundary layer over Ahmedabad. Now, we have seen day-to-day variation of the boundary layer, which confirms that short timescale response of the boundary layer due to solar flux, turbulence, convection, and winds. Now, in this figure, you can see that in February 1st to February 2nd and 3rd, like there is a huge there is a little variation of the boundary layer, which shows that the boundary layer can respond to the solar flux, turbulence, and winds variations very fast. Now, we have also done a monthly variation of the boundary layer, where you can see that the winter months show a shallow boundary layer height in comparison to the summer months. Now, a very interesting feature of the boundary layer collapse has also been seen during the monsoon. I will discuss more about it in the coming slides. Now, during winter, there is low insolation, thus the turbulence and mixing is less, which keeps the boundary layer lower at around 1 to 1.5 kilometer. During summer, the land temperature increases, and thus the sensible heat flux forces the boundary layer to rise at around 2.5 to 3 kilometers. Now, here in this figure, we have shown the difference between the summer and the winter months boundary layer height. We have noted that the boundary layer characteristics during different phases of the monsoon. We have seen that the boundary layer is initially thick during the onset of the monsoon, and somewhat, on some days it collapsed during the active monsoon, and again it started rising during the withdrawal of the monsoon. Now, this happens because of the cloud cover and the wet surface conditions. Now, in this study, we have also done a comparison of the oscillometer, which is a ground-based instrument, with other platforms such as radio sonde, cosmic GPSRO satellite, and ERA5 analysis. And we have seen that ERA5 is almost as comparable to the oscillometer data, but the cosmic GPSRO shows an overestimation, and also there were only 85 passes available on a 5x5 grid around Ahmedabad for the GPS-RO satellite. So it's very poorly estimated. Now, why is this study important? Like characterizing the boundary layer. Why is it important? Because you know that boundary layer is a very important input for many numerical models. So see, if you see in this figure, so if you use the ERA5 boundary layer, say suppose, you can end up with a lot of uncertainties, because we have seen that in this figure that ERA5 happens to underestimate the boundary layer. So when you want to do the local estimation of the radiative budget and all, so you have to put the correct boundary layer height values. That's why I think ground-based observations are really required. And of course, this is the first time that we have quantified the boundary layer over this region. So we are hoping for more of we are hoping to put this into the models right now. And as I have said already, I want to summarize again that we have seen the day-to-day variation in the boundary layer, and there was a winter summer difference of around 1 to 1.5 kilometer, and also during the monsoon season the boundary layer collapsed. And yeah, the boundary layer observations using the oscillometer are very important to improve such weather models, because as we have seen that there is also overestimation and underestimation using other platforms. Thank you.
Thank you very much, Sarita, for a very crisp and very clear presentation. Now the talk is open for a couple of questions. From chat box, I am not seeing any questions. Have you any time tried to, because we are using a oscillometer,
Yes.
the relation between boundary layer height and your aerosol distribution?
Yes, sir, this work is on progress. We are also trying to find the interaction with the clouds also. At the same time, I want to tell you that we actually cannot find out the aerosol properties using the oscillometer. For that, we have our Raman lidar. So we are like the work is ongoing using the Raman lidar, not the oscillometer lidar.
Yeah, very good, very good study. Continue the things. Thank you very much once again.
Thank you, sir, so much.
Now we'll move on to the next talk. Next talk is by TV Ramesh Reddy from SRM Institute of Science and Technology, and he'll be talking about atmospheric boundary layer height detection using the wavelet covariance transform. TV Ramesh Reddy. Ramesh Reddy, are you there? You have to unmute and respond. Yeah. Mr. Ramesh, are you facing any technical problem? You can, yes, it's coming, yeah. Yes, we could see your presentation. Go in full screen mode. Same problem. Yes, we can see your presentation. Go ahead. You have to unmute. क्या हो रहा है? Ramesh, you have to unmute your mic. Could not unmute. Like in your computer sound setting instead. Some problem is that sense.
I think this is a technical issue. We are getting back to you.
Yeah.
Ramesh sir, did you allow the browser to use your microphone input while using MS Teams from your browser? Can you type in the chat box?
Shall we go to the next step?
We will communicate with TV Ramesh Reddy and get to a solution. We request that the session chairs move on to.
Yeah, okay.
Thank you.
Yeah, I think Ramesh is facing some technical difficulties. We'll move on to the next presentation. It will be given by Ms. Pooja Sharma from Manav Rachna University, Faridabad, on variation of surface latent heat flux as observed during high magnitude earthquake. Ms. Pooja Sharma. Yes.
Sir, screen is visible?
Yeah. Screen is visible. It is in the full screen mode. You go ahead. Yeah.
Okay, sir. Good afternoon, everyone. I am Pooja Sharma, currently pursuing my PhD from Manav Rachna University, Faridabad. I am here to present my research work, Variation of Surface Latent Heat Flux as Observed During High Magnitude Earthquake. I would like to thank the organizer to provide me with opportunity to present my work. Now outlines introduction, data sources, data analysis and algorithm, result, conclusion, acknowledgements and references. First is earthquake is the final manifestation of the long-term process that occurs in the lithosphere under the continuous stress of plate tectonics. Based on the observation of prior to earthquake, some geophysical quantities, abnormal changes that anticipate moderate and strong earthquake within a defined spatial area according to lithosphere atmosphere ionosphere coupling model. One of the possible pre-earthquake effect, one of the effect could be the appearance of some climatologically anomalies in the epicentral region, be weeks, months before the major earthquakes. The methodology is based on the integrated analysis of more atmospheric and environmental parameters whose abnormal variation have been found to be associated with impending earthquakes. And lithosphere atmosphere ionosphere coupling model suggests that in the earthquake preparation phase, a variety of precursory phenomena occurs due to some exchange of energy. Various precursory signatures are observed over ocean land atmosphere due to seismic activities. Some precursors of earthquake at surface atmospheric ionospheric levels. First is surface level, surface parameters like surface latent heat flux, surface parameters, gas emanations from the underground to the surface, electromagnetic variations, groundwater levels, radon ion activity, ionospheric plasma perturbations. Therefore, the understanding and monitoring to various geophysical parameters and required to study the precursory signature for early warning and prediction of earthquake. And present work surface thermal parameter, surface latent heat flux has been analyzed for recent high magnitude earthquake. Data sources for this purpose, the detail of earthquake have been taken from USGS like United States Geological Survey, and data surface latent heat flux data have been retrieved from NCEP, National Centers for Environmental Prediction. We have worked details of the earthquake. We have worked on the recent earthquakes. This table shown details for recent earthquake activities which are nearly lying near the ocean. Table contains detailed information of the earthquakes, about the epicenter of these earthquake, and focal depth of the earthquake site is given. First event is 28 April 2021. Magnitude is 6.0. Earthquake occurred in Assam, India at latitude 26.781 degree north and longitude 92.457 degree east, depth 34 kilometer over a 8 kilometer of north-northwest of Dekiajuli, India. And second event is 17 July 2020, magnitude 6.1, latitude Port Blair, India at latitude 11.849 degree north, longitude 94.936 degree east, depth is around 10 kilometer. And third event is Ternate, Indonesia, 14 November 2019, magnitude 7.1, occurred in Ternate, Indonesia, latitude 1.621 degree north, longitude 126.416 degree east, and depth is 33 kilometers. And fourth event is 24 June 2019, magnitude is 6.1, and latitude Evapura, Indonesia, latitude is 2.776 degree south, longitude 138.568 degree east, and depth is 28 kilometer over the 230 kilometer west of Evapura, Indonesia. Analysis of the surface latent heat has been done through climatological analysis for seismic precursor identification, that is Capri algorithm. The appearance of seismic precursory usually occurs on large scale area around the impending faults, and circular size of thermal precursors and magnitude of the eventual earthquake, like first equation, rho equal to 10 की power 2.43 mag m, where rho is the radius in kilometers of the interested area and m is the magnitude of impending earthquake. The scope of this algorithm was searching for anomalies of the time series for climatologically parameter by the statistical analysis. We describe the procedure only for the surface latent heat flux. Then equation number 2, the data especially average using only those over the land, where TDY is the mean value of surface latent heat for the specific day. D is the day, and in year 38 year, and lambda and phi are the latitude and longitude, and triangular bracket stands for spiral average. First of all, adopted Capri algorithm remove the long-term trend over the whole day-by-day data set. This procedure is used mainly to remove a possible global warming effect. To remove this trend, each time series corresponding to the same day over all the 38 year is analyzed separately, performing a linear fit of the studied variable for a single day of the year along the whole period, and the fit slope is then used to remove the long-term variation of the variable analyzed. Equation number 3, where first year y naught of the time series is used reference, and subsequent year the increasing of the variable given by the product of slope of the fit by the consecutive number of year from the first of the series is removed. Then this procedure is repeated for all the analyzed days. The advantage of carried out the different fit of each days is to take a possible different seasonal local effect over the year. Note that although the 2021 in Assam did not contribute to the estimation of the long-term trend, we removed found trend also that year. For each day, the data of the time series are averaged over all the years. Equation number 4, THD, average temperature of the particular day in the past 37 years. Because we now exclude earthquake year of the investigated seismic sequence. Now NY, where NY is the total number of averaged year, for each day the algorithm calculate the standard deviation. Variable behavior of the year in analysis is then compared with the historical series, equation number 3. Then equation number 5, our operations serve to discriminate the short time anomalies that we are looking. Anomalous days are defined as those days for which the value of considered variable overcome its mean by at least 2 times standard deviation. Then we check the 2 times standard deviation anomalies more than a day. Now result, first is Assam. A significant change of the surface latent heat flux has been observed prior to the seismic activities. Variation of surface latent heat flux are shown in figure, this figure and figure 1. Red line, broken red line, which is scattered time series, shows maximum surface latent heat flux, and solid black line with scattered shown historical time series, and colored line green line indicates 1 standard deviation, yellow line indicates 1.5 standard deviation, and blue line indicates 2 standard deviation from the mean of the historical time series. This figure shows that as statistical analysis, this figure describes the comparison between time series 2021 and the historical data from 1984 to 2020 time series has been done. Shown range in x-axis 2 months starting from 28 Feb to 28 April. So note that surface latent heat flux is increased on starting 5 March, 6 March, 15 March, 21 March, 29 March, and so on. After that, again 13 April to 26 April, and surface latent heat is greater than 2 sigma, that the historical mean for the same days. Earthquake sequence was analyzed in terms of surface latent heat flux for the period of 2 months and compared with the last 37-year trends. Now we are concentrating only on the anomalous behavior where the surface latent heat above 2 sigma, 2 standard deviation. So why we take 2 sigma? Because the data when we see the bulk up and the Poisson's ratio, 95% of data is covered. Second event is Port Blair in on 17/7/2020, and statistical analysis describe the comparison between time series 2020 and historical data 1983 to 2019 time series has been done. shown range starting from 2 months, that is 19 May to 17 July. First of all, we can see that surface latent heat is greater than 2 standard deviation initially on date 19 May. After that, surface latent heat is greater than 2 sigma, then historical mean for the same days on date 25 May, 28 May to 3 June. After again greater on date 7 June, then 17 June to 30 June. And again greater than 2 sigma than the historical mean on 7 July to 17 July for the same days. It shows that again the pre-earthquake climatological anomalous behavior. Next event is Ternate, Indonesia, 14/11/2019. Historical data from comparison between his time
you
series.
have 3 more minutes.
Okay, sir. Okay, sir. 20, in this figure, standard deviation seen more than greater than 2 sigma, 18 September to 21 September, then 3 November 2019 to 6 November, again 12 November for the same days, and again this shows the climatological anomalous behavior of the surface latent heat flux. Now figure 4, Avepura, Indonesia, and Indonesia surface latent in this figure from range 26 April to 24 June. Surface latent heat is greater than 2 sigma, date 1 May, 2 May, and then 7 May to 10 May. After that, 22 May to 25 May, again greater on 29 to 31, and 4 June. Again, maximum surface latent heat is greater than the historical mean of 7 June for the same days. So overall, we can see the anomalous behavior of surface latent heat flux in all figures prior the main earthquake events, that is 2 months. Now conclusion, the behavior of surface latent heat flux in the epicentral region shows an almost similar trend for all 4 earthquakes events 2 months before main earthquake events. Anomalous behavior is found where the surface latent heat flux is above 2 sigma, and we have tried to take the same depth, but due to proximity of ocean, heat transfer will only vary the value of surface latent heat flux, and increase in the surface latent heat flux prior to the main earthquake event may be attributed to the thermal infrared around the epicenters and near surrounding the area. Therefore, infrared radiations, all it's feel that it might be due to this reason, and proximity from the ocean is also to be the reason for the varied behavior of the surface latent heat. Now, acknowledgement, the corresponding authors are thankful for providing necessary motivation of complete this research work, and surface latent heat data has been downloaded from NCEP, and details of earthquake has been taken from USGS and references, and thank you.
Thank you very much, Pooja Sharma, for a very detailed presentation on surface latent heat fluxes. Now the talk is open for questions. I am not seeing any questions from the chat box. Okay, do you know any direct measurements of latent heat flux around these areas? Direct, you have taken from NSAP NCAR, but
Yes,
there are
sir,
some
yes.
direct measurements of latent heat flux. Did you
Yes,
try
sir.
it? Yeah.
Hello.
Did you use that?
Hello.
Hello.
Hanji.
I am asking whether the direct measurements, because you have taken from NSAP NCAR instead of NSAP NCAR, whether nearby any sources for lands this one latent heat flux. One more question. Hello. And one more question is from Nirvikar. I think Pooja, are you there?
Hello.
Hello, Pooja Sharma, are you hearing us?
Sir, actually technical problem, network issue है. एक minute. Voice
Okay.
is not clear.
Yeah. Okay, Pooja Sharma. Anyway, it's a very nice talk. Continue with your work. Now we'll move on to next talk. Ramesh, could you solve the problem? Still it shows you are muted.
Ramesh Reddy sir, are you here?
I think he's disconnected, it seems. His name is not appearing in the participants list. In this case, we'll move on to the next talk. Next talk is by V. Kirti from NRSA, ISRO, Hyderabad. She'll be talking about impact of COVID-19 lockdown on land surface albedo and associated climate variables over metro. Oh, I think this title is cut here. Now I invite Ms. V. Kirti. Yeah. Kirti? Yes or not there?
V. Kirti has withdrawn her talk. So maybe we can move on to the next
Hello, ma'am.
speaker.
How it is audible? This is Ramesh Reddy.
Yeah, Ramesh, we can hear you.
Yes, sir. Actually, I joined with my brother account, Rakesh. With one profile, I joined. I am presenting with this account.
Okay, okay, then no problem. Just try to share your presentation.
Is it visible, sir?
Yeah, we could see your screen. Go to full screen mode.
Yes, sir.
F5. Ramesh, press F5.
F5. Sir, actually, this is the Apple function. Yes, sir. Sorry. Sorry
okay, yeah. Fine, go ahead. Yeah.
Yes, sir. Good evening, everyone. Myself, Ramesh Reddy, working as a senior research fellow at SRM Ministry of Science and Technology. Today, I am going to present on diurnal variability of atmospheric bound layer during different seasons or tropical east coastal station pattern closure. So, introduction. The bound layer is the lower part of troposphere, which is directly influencing surface forcing within a time scale 1 hour or less. The layer is characterized by turbulent motions that transport the momentum, moisture, and other atmospheric pollutants horizontally and vertically throughout the layer. The atmospheric bound layer depth depends upon the surface wind, surface heating, vertical variation of wind, and mix of pollutants. And this high frequency occurrence of the bound layer near to the ground makes the bound layer different from the rest of the atmosphere. So, depending upon the physical characteristics, the diurnal variability of ABL is classified as the three sublayers, that is convective, daytime convective bound layer, and nighttime stable bound layer, and above the stable bound there is the residual, which is the daytime dominant part of the convective bound layer. So this daily cycle atmospheric bound layer over the land surface, but along the coastal region, due to the frequent occurrence of the sea breeze, within the bound layer there is one more internal bound layer zone, which is the thermal internal bound layer. So over the coastal region, due to the frequent occurrence of sea breeze, the bond layer is affecting this due to the sea breeze, and bond layer growth is reducing. So in this study, I have three data sets. That is, one is a micropulse lidar data, which is installed at SRM IST during the in January 2016, and it have my 530 nanometers wavelength laser and 3 to 4 micrometers wavelength, and fault reflection frequency is 2500 inches. And along with that, I also used the radio sound data and AWS data, radio sound data for identification ABL height and AWS for identification sea breeze during the different seasons. This AWS data and IMD radio sound data is collected on the IMD Chennai. So for identifying the ABL height, there are several methods is available. So for in this study, I have used the wavelet covariance transform method. So this formula representing the WCT method mathematical representation. Here, FZ is the lidar NRB signal, and H is the Haar wavelet function. And here, this figure 1 is showing that on typical profile of lidar NRB data, and B is showing the Haar function, and C is showing the different signal vector, different dilation parameters, and ABL signal wavelengths WCT profiles. So, and here results and discussion. First, I'm showing this surface meteorological condition over the SRM location. Here, figure this wind rose plot showing the surface wind direction during different season. Here, during the winter and post monsoon season, the observational location is mostly influenced by the northeast synaptic winds and maybe sea breeze. Whereas in the pre-monsoon season, the observational location is mostly wind is coming southeast to east direction, and it is mostly because of sea breeze over this location. Whereas in the southwest monsoon season, the observational location is frequently influenced southwesterly winds, and very few times we are observing the sea breeze. And figure E and F is showing the surface temperature and RH during different seasons. Here we are observing during the winter and post monsoon season, the surface temperature is less and maximum attains at 1 o'clock. And similarly, in the pre-monsoon and summer monsoon season, the maximum temperature attains at 13 IST. And whereas the RH is showing the maximum in northeast monsoon season because of frequent occurrence of rainfall, and rest of the season is showing the dry less compared to others. And this figure is showing the evaluation of atmospheric bond layer during different seasons. During different seasons, the first figure A is showing the typical case of ABL identification during the winter season. Here, we after sunrise, due to the surface heating, the bond layer is growing and it's attaining maximum at 1 o'clock. And this is from obtained the lidar NRB. And at the same time, that morning itself, the observational location is identified the sea breeze condition. So it is because of sea breeze effect, the bond layer growth is less in this season, and is showing the less growth. And after that is after sunset, the bond layer is converted to SBL and is started to decreasing with time. And whereas in the case of pre-monsoon season, after sunrise, the bond layer is started to evolve and attains its maximum 1 o'clock. At the same time, around 13 IST, the observational location is started to influence by the sea breeze. It is shown in here with wind vector plot. Here we observed after the onset of sea breeze, due to the sea breeze onset, within the convective bond layer, there is the internal bond layer found. We can clearly see from here. And after the sunset, due to this TABL considered as the SBL, and above the daytime convective bond layer is considered as residual layer in this time. Whereas in southwest monsoon, throughout the day, observational location is influenced by southwesterlies only. So the internal bond layer is not yet observed, and the bond layer attains maximum at evening, and even temperature also we can see at maximum attains afternoon around 16 to 17 IST observed in this season. And after the sunset, after 2 hours of sunset, we are observing the SBL here. And similarly, during the post monsoon season also, we are observing that less convective bond layer growth due to the surface cooling as well as the northeast synaptic wind as well as sea breeze. So here during the winter and post monsoon season, the observation location is observed less ABL height, whereas the pre-monsoon season we are observing because TABL afternoon here, and whereas southwest monsoon season the observation is deep convective bond layer observed in this case. And here I'm showing the diurnal variability of ABLH and formation of TABL during different seasons. And here during the winter season, we are observed the around 13 IST the TABL observed here, and after the TABL, the convective bond layer is showing the last standard deviation, which is because TABL above the converter model. This is the nighttime residual observed. So during different seasons I have shown here, and the maximum percentage of occurrence TABL observed during the pre-monsoon season and minimum during the southwest monsoon and northeast monsoon seasons. And here I'm showing the statistics of TABL and RL and SBL during different seasons. So here we are observing the maximum SBL height during the southwest monsoon season and minimum during the post monsoon season. Actually, we don't have below 300 meters. The LiDAR have a limitation. Due to that, we are not able to identify the large. We are not able to see the strong seasonal variability in the SBL and TABL case. So up above 300 meters only we are able to identify. With this, we are observing the maximum SBL height during the pre-monsoon season, southwest monsoon season, and minimum during the winter season. And TABL observing the maximum height during the pre-monsoon season and minimum in southwest monsoon season. And in the case of SCBL, here we can able to see the strong seasonal variability during different seasons. We are observing maximum SCBL height during the southwest monsoon season because whereas in the pre-monsoon and post-monsoon season, we are rest of seasons we are observing less CBL height. During the winter season, we are observing less convertive bond height. And similarly, we are observing RL also similar way, or we are observing maximum RL during the southwest monsoon season and minimum during the northeast and winter seasons. And here I'm showing the growth rate and decay rate of the ABL during different seasons. During the winter and post-monsoon season, the growth rate is maximum within the 100 meter per hour, and decay rate also same in the 100 meter per hour. Whereas in the pre-monsoon and southwest monsoon season, the growth rate is above 50% is above 200 meter per hour, and decay rate also is falling same, which is due to the during the pre-monsoon southwest monsoon season, the surface convection is more. That's why the convection is more strong in this season. That's why it is showing the maximum CBL height in this maximum growth rate above 200 meters. So this is showing the mean dynamic variability during the different seasons in this figure. So in this during the winter and pre-monsoon season, post-monsoon season, the maximum ABL height observed at 1.5 kilometer at 13 IST. Winter and pre-monsoon season, the mean ABL observed 30 surface mean maximum ABL and TS observed at 13 IST, whereas southwest and northeast monsoon season, the maximum ABL surface observed 14 IST. Overall, the maximum ABL height observed during southwest monsoon and minimum during the winter minimum during the winter season. Here maximum actually we used to observe the maximum SBA convective bond layer height during the pre-monsoon season because surface strong surface, but this observational location is strongly influenced by the sea breeze. That's why you are observing southwest monsoon is the maximum convective bond layer height. Summary and conclusion. In this paper, we have studied the dynamic variability of coastal atmospheric bound layer using high resolution microscope or optical station. The main findings are summarized below. The frequent occurrence of TABL leading the decrease of ABL in early afternoon hours 13 IST during the winter and pre-monsoon season, and late afternoon hours 14 IST during southwest and northeast monsoon season. In total, found the SBL forms more frequently during the northeast monsoon season and less frequently compared to other seasons. The RL forms more frequently southwest monsoon, minimum during the northeast monsoon. The maximum SBL and CBL height observed during southwest monsoon and minimum during northeast monsoon season. And the maximum growth rates are 50% above 100 meters per hour during the winter and post monsoon season. In the pre-monsoon southwest monsoon, the maximum growth rates are between 100 to 200 meters, and all the season decay rate is 100 meters per hour at maximum. The maximum ABL height observed during southwest monsoon season and minimum during the post monsoon season. And the seasonal mean maximum observed at 1430 IST during the southwest monsoon, and rest of the seasons we are observing maximum mean ABL height 13 IST. Reference. Thank you, sir.
Thank you very much, Ramesh, for discussing a new technique to identify the boundary layer. Now the talk is open for questions. From chat box, there are no questions. If anybody want to ask questions, they can raise their hand and go ahead. So if there are no questions from the participants, Ramesh, can you tell me what is the advantage of this wavelet technique compared to the conventional technique in identifying the boundary layer height?
Yes, sir. Actually, in wavelet technique, we are increasing the dilation parameter, and we are changing that we can able to identify we can able to clearly identify the ABL height. Whereas in the normal methods, suppose gradient method, we are getting multiple gradients, so we cannot which one we have to take the ABL, we are not able to. But here by increasing the wavelet, we can able to correctly choose the ABL height with the changing dilation parameter.
Okay, good. And do you have any idea why northeast monsoon we get a shallower boundary layer height over the observational site? It's over Chennai, right?
Yes, sir, over Chennai, sir.
Yeah.
One reason is that northeast monsoon is the heavy rainfall we used to observe in the Chennai, sir. So,
Yes.
and one more thing is the frequently are observing that northeasterly surface winds. So it is making the cooling the surface, and as well as it's not allowing to grow the ABL height, ABL convective ABL, it's not growing that much. Mostly because of rainfall, and one more is the sea breeze. Sea breeze are northeastern applications.
How do you think that rainfall decreases the ABL height? In which process? Physical process?
Physical process, we are surface heating will be less due to that. When it's the wet surface, we will get less surface convection, so it's making.
Yeah, the wet surface will have a big, you have a, whatever your surface fluxes will be reduced. Because whatever solar heating, it will be utilized for latent heating as well as sensible heat.
Yes, sir.
That's why you'll be getting a shallower. Good. Yes. Good presentation, Ramesh. Keep it up.
Thanks.
Yeah. Now we'll be moving to the last presentation of the day, and for the session also, PS2 will be coming to end after this presentation. Now I invite Arshini Saika from Dibrugarh University to present her work on decadal changes in atmospheric methane emissions over the eastern Himalayan region, source apportion. Arshini, are you there?
Yeah. Hello, sir.
Yeah. You are audible. Now share your presentation.
Hello, sir. Hello.
Go to full screen mode. Yeah, we could see your presentation. Go ahead.
Good evening to one and all. Myself, Arshini Saikia from Dibrugarh University. I will be talking about the decadal changes in atmospheric methane emission over the Eastern Himalayan region, source apportionment and impact assessment. Among the greenhouse gas, we are motivated to study and understand methane emission and its impact over the study region because it is the short-lived and can trap more heat than carbon dioxide in the atmosphere. It is 28 times more stronger and efficient climate forcer compared to CO2. It's not only act as a greenhouse gas but also produce other greenhouse gas such as carbon dioxide, ozone and precursors in the atmosphere through chemical reaction. It also impacts health, causes respiratory, heart and lung diseases and also impact agriculture and ecosystem. According to Climate and Clean Air Coalitions, global methane emissions are contributed from various sectors such as agriculture 42%, fossil fuel 36%, waste 18% and other sources 3%. In our study, we use methane as a climate change indicator for which we analyze several datasets, and here we present the column average methane concentration from Syamaki and Goset satellite, and we found an increasing concentration of methane over time globally in northern hemisphere and in the study region, that is Eastern Himalayan region. And also from several literature, we found that the methane is increasing since the pre-industrial period. And here I am giving one example. Villorin et al. 2020. They published a paper where they found that methane increased by 157% over the period 1750 to 2018 globally. And according to the recent IPCC report, that is IPCC Assessment Report 6, temperature changes about 0.6 degrees centigrade due to change in methane from 1750 onwards. Here I am showing the study region, the Eastern Himalayan and Foothill region, which extend from 86 degree to 100 degree east and 20 to 32 degree north. This region is very rich in natural resources such as oil, gas, coal, petroleum, etc., which you can see in the map. Apart from these sources, there are other sources such as brick kiln, cement factories, which are highlighted in the map. And for this study, we used several data sets to understand the changes in the emission, the concentration, and also to reduce the uncertainties in for a particular data set result. So the methane surface concentration and column average data are taken from Copernicus atmosphere monitoring services. The air temperature at 2 meter is taken from ERA 5 land data product. The column average methane are the observed column average methane data is taken from Siamaki and Goset satellite with a spatial resolution of 5 degree into 5 degree from Copernicus climate change services, and we use Siamaki 5 model to predict the future projection of methane and also to study the surface temperature. And here are our results. The major sources of methane and their percentage contributions are presented. We use Edgar and Kemp's dataset to study the several sources of methane and their contribution over the study region. And in Edgar dataset, we group several similar sectors or sources, and we finalize and we combine and finalize into 6 categories, which are presented as transportation, energy, industries, waste, agriculture, livestock, and from camps. We used sources such as wetland, biomass, burning, anthropogenic, total anthropogenic, and anthropogenic plus biomass. We use camps in addition to Edgar because the emission from wetland and biomass burning are not available in the Edgar anthropogenic inventory data set. In Edgar, we see the emissions are increasing from 1970 onwards from all these sectors except for agriculture. In agriculture, we see that during 1970 it is 23%, but in 2012 it goes to 19%. But the magnitude is significantly high compared to other sectors in agriculture. And similarly, in CAMS data, we see that biomass burning, anthropogenic and anthropogenic plus biomass burning, we see that the emissions are increasing, and in 2016 it is more than double compared to 1990. We also see the impact of change in land use land cover over the study region, how the land use land cover changes also impact the emission of methane. Because as we know that forest and grassland, if the forest and grassland are there, then there will be more net consumption of methane. But if there is more wetlands, then there will be more emissions of methane. But when we just analyze the data set from Moody's for the year 2001 and 2018, this is 2001 and this is 2018, and sees the bias between these two, and we see that that the forest area is decreasing by 0.4%, and wetland is increasing. Wetland is increasing by 0.09%, And if the forest area is decreasing, it means the net consumption of methane is also decreasing. And if the wetland increasing, means the emission of methane is also increasing over the study location. Also here we see the scenes, this is the Bangladesh, which is having close proximity with the study region, that is the Eastern Himalayan region. Here we see the means large change, and in the northern part of the study region also we see the high amount of change. Next, we analyze and see the spatio-temporal distribution of methane emission for various data source, that is CAMS, EDGAR, and RCP 8.5 emission dataset for different time period. And here we see an increasing trend of methane for all the dataset, and the Eastern Himalayan, the increasing trend in Eastern Himalayan region is more compared to the global trend. And in CAMS, we see an increasing trend of 0.08 teragram per year. And for EDGAR, we see it approximately 0.1 teragram per year. In case of RCP, we see 0.16 teragram per year. Next, we see year-to-year changes in the column as well as surface methane concentration using different data sets and its impact. This is the observed one, that is Siamaki and Goset satellite data. This is CAMS columns average methane, and this is CAMS surface methane, and this is the model methane data. Here, in all the data set, we found that even though the time periods are different for all the data set, but all are showing the increasing trend of methane both globally and in Eastern Himalayan region. Here, here we can see the for Siamaki and Goset that increasing by 0.17 ppb per year globally and 0.02 ppb per year in the Eastern Himalayan region. Similarly, CAMS column average also 1.11 ppb per year, and for in the Eastern Himalayan region is 0.88 ppb per year, and surface concentration and 5.13 ppb per year for global and 6.48 ppb per year in the Eastern Himalayan region. In CIMI 5, 13.37 ppb per year global and 14. Here in the surface concentration in both CIMI 5 model and in CAMS, we see the trend in the Eastern Himalayan region is more compared to the global. This is attributed to the sources, near surface sources, which is present in the region. Now, to understand the impact of methane, first of all, what we do, we check the changes in the surface temperature over time for total anthropogenic activities. It's not for methane, or it's not for a particular gas or aerosols. It is the total change because of the anthropogenic activities. And what we found, this is the global, and this is, we take the data from ERA 5 for the period 1981 to 2019, and we divide the period into two time frame, that is from 1981 to 2000 and 2001 to 2019. And we took the bias for the global as well as we took the bias for the regional. And the bias plot, so this is showing the positive bias. It means the temperature is increasing both globally and regionally. Here I am giving that an increase in the global mean temperature of 0.6 degrees centigrade from which is 8.857 degrees centigrade during the period here 1981 to 2000 to 9.818 degrees centigrade during, means if we divide the two time frame and we take the bias, and we get that it is increasing with time. And similarly for the study region, we get an increase of 0.3 degrees centigrade. Now we took the time series for area average time series map, and we see the surface temperature anomaly, and here also we get an increasing trend of methane both in globally and regionally. And in case of CMIB5 model, we see that the predicted future projection map is trend is more stronger and higher compared to the historical period. Now we estimated the global and regional methane only due to methane radiative forcing and the changes in the temperature due to methane, for which we calculated using the following formula, which is derived in Etminian et al. 2016. Here A3 and B3 are the constant, and M naught is the initial condition of methane, and M is the final concentration of methane. And N naught, we also need N. N naught is the initial concentration of nitrous oxide, and N is the final concentration of nitrous oxide. So with this equation, we find out the radiative forcing due to methane for global as well as for the regional. And after that, what we do, we take another equation which is given in the Huntingford and Cox 2020, and this is the equation. From here we can derive the change in temperature due to particular, because del Q naught is the radiative forcing which we will get from here. So if we substitute the radiative forcing here, then we will derive the change in temperature due to methane. And using this equation, we can derive. Here K is the effective thermal diffusivity, and Z is the depth in the ocean positive downward, and del T.
Arshini, you have 3 more minutes to conclude.
Okay, sir. And del T1 is the change in the surface temperature over land, and del T naught is the change in the surface temperature, sea surface temperature. Lambda 1 is the climate sensitivity of model over land, and lambda naught is the climate sensitivity of model over the ocean. F is the grid box fraction of Earth's surface covered, and nu is the land sea temperature constant in warming, and K is the ocean diffusivity. This in this paper is already derived values, so here only we need to know only one variable, that is del Qt, with the help of which we can say we can calculate the change in temperature. So with this equation, we just calculated the radiative forcing due to methane as well as temperature change due to methane, which is shown in here, surface temperature. And what the result we get, we access an increasing trend of temperature over land induced by methane at the rate of 0.0036 degrees centigrade per year. This is global, and 0.0062 degrees centigrade per year over the Eastern Himalayan region. And in radiative forcing also, we found an increasing trend of 0.0057 watt per meter square per year over the Eastern Himalayan region at a rate of 0.0061 watt per meter square per year for the Eastern Himalayan region. So this is the summary of our study. The decadal methane emissions and trend on the regional scale are stronger than the global scale. Anthropogenic source contribution to increasing the methane emission over the Eastern Himalayan region is more than the natural sources, and methane-induced radiative forcing and resultant temperatures trend are stronger over the Eastern Himalayan region than the global trend, and the predicted global radiative forcing and the temperature trend are higher than the historical trend. Overall, the global and regional atmospheric surface concentration of methane has risen significantly over the last few decades. Also, from the RCP 8.5 scenarios, the emission will be increasing by twofold by the year 2050, and which will be further, if the emission is not stopped or if the mitigation is not taken, then it will be further increased by threefold by 2100. Thank you.
Thank you, Arshini, for a very nice talk and very elaborative and very informative talk. Most of people in India was focusing on carbon dioxide, and you have took for these methane observations. Now the talk is open for questions. Already have seen one question from Aravind Vel. He was asking methane increment you have looked in RCP 8.5 is any specific reason, and what was the trend for RCP 4.5?
We choose RCP 8.5 because it is the business on scenario where where there will be the maximum emission. We have not chosen other emission scenario because we want to check that at maximum level what will be the extent of the emission. And in RCP, if we check the RCP 4.5, or then we will get it reduced by 20% or 30% compared to the RCP 8.5.
Yeah, okay. Any other questions? If there are no more questions, I have one thing. Whether you compared this future projection of increasing temperature, it's very good that you have alone CH4 how much contribute you have shown. With comparison to CO2, how it stands, it is more or less?
Sir, it is if we see like a scale, time scale, then it is more for methane. But if we see in long term, and then carbon dioxide is more.
Okay, okay, that's good. If there are no more questions, I thank Ashini for a very good talk. With this one, we come to end of this, not only this session, this plenary session too. For last 4 days, you had a very good talks. Today, I will take this opportunity to thank all the speakers and the chair of this session, first session, Dr. Balasubramaniam. And it was from kaleidoscope of presentations, starting from stratosphere, troposphere, boundary layer, and trace gases. Most of them were very informative. And I thank all the speakers, not only for this day, all the last 4 days. And I take this opportunity to thank all the co-conveners of PS2, Dr. Tarun Kumar Pant, Dr. Balasubramaniam, Dr. Nirvikar Dashora of NERL. And I also want to thank LOC. They're really very helpful. And I have never saw a moment where we just spoke LOC and there was a response within a second. I think you are at a workstation all the time. We thank you very much. And on the lighter side, I suggest you can open a startup for conducting scientific events. So back to LOC. I thank once more all the speakers and all the participants of this session. Back to LOC.
Thank you so much, Dr. Kishore Kumar and Dr. D. Balasubramaniam. Thank you for chairing this session and engaging us with all the information and helping us to moderate this session. We would like to thank all the speakers of PS2, and we hope that everyone has had a good and interesting, informative time. So with this, we come to the end of PS2, and we will now be closing the session. We thank everyone once again, and we hope that you will be joining us for the closing ceremony, which is scheduled tomorrow. For this, you can join the closing ceremony link, which is provided to you on the information kit. So